¿Hola? ¿Se oye? Sí, ¿no? Creo que sí.
Sí, sí, sí. Hola.
while we wait for some more people to join, we have a request. So some people need to go to the desk here to get a ticket for dinner. Yeah, a green ticket for the dinner. So if I say your name, please at some point go to the desk. Eduardo Bataner, Remus Valentin Joan. Sorry if I mispronounce anything. Oh, some names, some surnames. Rafael García Uceda, Mervis Wout, Sebastian Korsak, Madalina, Adrian Roik, and Herbert Levin. I think this is if you made some request for a different meal, different menu for dinner, they will give you some voucher here. And I think we can begin with our afternoon session. We start with Roberta Sambrini, who is coming from IFISC in Palma de Mallorca, and she's going to talk about quantum complex systems for machine learning.
Hi, can you hear me? For the registration. Okay, so it's a pleasure to be here, and I thank you for the kind invitation. And I'm, as Anatol, I'm from the IFISC Institute for Disciplinary Physics and Complex Systems, where many topics that are being actually treated in this event are studied, and in particular I work in the quantum line. So there are 5 research lines, and I work in the quantum line. So as at the end, typically there is no time. I started with the slide with the collaborator. These are some of permanent and so permanent PhD, postdoc, and previous collaborators that are that have been at the institute or are in other institutions. And the work I'm going to present today, I'll try to put it in a map, is about quantum reservoir computing. So let's start from a map from a broader context. You can do computation in a typical way, that is with digital systems, but you can do computation also with analog systems. And analog systems have been used from the past, and in quantum configuration, these analog systems are typically used in the context of quantum simulations. So this dualism between digital and analog approaches is also present in machine learning. So in machine learning, you can have, for instance, in the case of quantum machine learning, you can have very popular approaches that are based on variational quantum algorithms, in which you have a quantum circuits and you optimize the circuits through some kind of task iteratively. Or you can take, let's say, a more analog, brain-inspired, neuromorphic, as you want to call it, approach, in which you actually use a complex system, and you see under which condition you can use this complex system to process information. So this is the point of the map in which quantum reservoir computing falls. So it's analog, and in particular in this talk it will be quantum. But before to go to that, 2 words about classical reservoir computing example of complex systems. So this is just a list of possible settings that have been studied. You see there's 9 more networks. Water bucket, this is pretty popular. Do reservoir computing with a bucket of water. Optical cows, MEMS-driven strings, spintronics oscillator, chemical oscillators. So different systems have been used actually to do this kind of as reservoir for machine learning tasks. And in particular, reservoir computing, we will see it's well suited for temporal tasks. So in this context, recently, quantum reservoir computing has been proposed as an alternative. And the idea of this talk is to introduce you to reservoir computing, classical and quantum, and then to show you some of the complex quantum reservoirs that have been considered for reservoir computing. And if there is time at the end, speak about a major issue in quantum reservoir computing, that is the problem of measurements and monitoring. Okay, so let's start with reservoir computing. I assume that not all of you are familiar with it, so I start with an introduction. So the idea of reserve computing is that you use a system to do supervised machine learning. Supervised means that you have data that are labeled, and so you have a training phase and a testing phase. And this is used to do typically temporal tasks. So these temporal tasking sometimes is confusing. So let's spend just 2 seconds on this. What does it mean, temporal task? You can have, of course, temporal data of any kind, and you can process them just giving your vector as an input, as a static input to a system, and then you calculate an output. I would not call this a temporal task in the sense that you have a string of temporal data, but your processing is actually static. You have an input and an output. When we speak about temporal task, we refer to the fact that this is online. So if you have a string of data, data are actually injected into the system sequentially. And after each input is injected, you do a part of your analysis, and you do this online. So this is the meaning of temporal. Okay? So example of temporal task, a very popular example, of course, is speech recognition. If you have a device that is doing speech recognition, needs to process the data as long as they are arriving. The processing window needs to be long enough to recognize word, but you don't want this to be too long because you want to make sense of the finite amount of that. So you have something we will see later is a fading memory. So this kind of tasks require at the end a memory inside your processing system, because actually the system is receiving data, remembering information of the previous one, and processing the new data using this memory. So you speak about in-memory processing. And this is a major feature because this avoids to have what is called the von Neumann bottleneck, that is the fact that if you have an external memory, you have to access this memory, and this can cause a delay in your processing, while here the idea is that you have a system with an internal memory. It's complex, so it actually processes an internal memory that you can exploit for this. So what are the first kind of proposal? I put this just to give an idea, because if not, at least a formula, some formula we will need to put them. And here what we have are the two first proposal of what is now called reserve computing. This was called eco-state network, and there was at the same time another proposal that was this liquid state machine. And in this eco-state network, what you have is that the state of reservoir at time k is given by some nonlinear, typically sigmoid activation function of the previous state of the reservoir and some input data that are sequentially injected as a Gustavian effect. So when you have this, you have actually a map that is evolving, and then you take at the output layer a function of these reservoir observables. And typically you take a very simple observable, so you can do actually a simple linear regression of that. So this is what is called the eco-state network, and despite of being so simple, it has actually been shown to be successful in many time series processing tasks. So the general sketch of reserve computing going beyond the eco-state network, but in general setting, what you have is a mechanism for input injection, a substrate that is your bucket of water or any system you are considering as a reservoir. And then at the output, you read out some of the observable and you do a very simple training. So you take, for instance, just a linear combination of the output, and then you just try to optimize this linear combination of the outputs toward a certain task. Okay, so you do a linear regression to optimize this, minimizing your discrepancy with the target. So with respect to neural networks, this is extremely simple because everything relies actually on the complex dynamic of the system. So for people that are coming from physics more than from computation, it's fun because everything is actually relying on the physics of the system. At the output layer, you're just doing a linear regression, okay? And moreover, from the more applied point of view, it avoids the burden of backpropagation to time in neural networks that is extremely consuming. So this is the main advantage of the cyber computing, a very simple training. Okay? And also, you see the memory arises because at each time step, you have the reservoir is a function of the previous one. So you actually have a chain, and you can see that the memory remains into the system. While if you have something that works just processing inputs, not requiring any memory, you typically speak of extreme learning machines. And these are used, for instance, for classification tasks. Classification tasks are not temporal tasks. You do not need to establish an order of the data that you are injecting. You just need to classify them. It doesn't matter if you receive a cat before a dog or not. You just need to recognize the class of the image you are receiving. So this is a list of some of the application of classical reservoir computing. It is pretty large. It is also various. Many systems have been used, and it was been very successful in the last at least 10 years. In many, typically, most systems are optoelectronic and optical systems. This kind of, let's say, competitive applications. So out of fun, the applications that have been successful on this kind of platforms. So brief summary, what is reservoir computing is a supervised machine learning approach for time series processing. It is suited for analog implementation, and it is based on the fact that you have a system that is complex enough to be to have a high dimension, to retain internal memory of the input, and to be nonlinear, and to be able to do processing. Yes? The, sorry, did I didn't enter? You do the training over a whole training unit. So you have a temporal series, and you establish your training window. So you have, I don't know, 10,000 data. You use that for the training, which are optimized over all these. And then once you have that, at each time step, you continue to proceed. So there are no epochs. It's just something that you do once. Okay? And so advantages, I was telling, this. The training is fast, and linear regression is typical enough. It's energy efficient, therefore, and it's also multitasking, because the only thing that you have to change if you want to do different tasks with the same temporal series of input, you send the temporal series of inputs and you are the output. And then you can optimize the output towards different target tasks. And you do not run the system again. It's multitasking in this sense. You just do different linear regression. So it's multitasking in this sense. Okay, so what is quantum reservoir computing? You can imagine. You put quantum everywhere. And then, so you will have a quantum reservoir for starting. So you typically have reservoir computing in which you actually replace your reservoir with the quantum systems that you are good enough to control in your lab. And in the input, you can also have either classical or quantum input. So this is one of the major feature of quantum reservoir computing, that you can also deal with quantum inputs without doing the full tomography of the quantum state. And at the output, you can do different kind of observables, and in particular, two main things can be continuous variables observables, like it could be, for instance, the amplitude of an optical signal, or you can have discrete variables. So if you have single photon detection, for instance, so this kind of things. So you also have quite a lot of flexibility there. So this would be the typical, the more general thing. Which was the first proposal? The first proposal was a few years ago, 2017, and it was done by Fuji and Nakajima. So what did they propose? They proposed to take a model of coupled qubits and use this as a reservoir computing, mentioning what were already seen as major advantages. So if you have a quantum systems and you have n qubits and nodes, you have an exponential number of degrees of freedom. So the degrees of freedom here are actually what are taught as the real neurons of the system. So the major advantage that is seen using quantum system is a dimensional advantage. I'm not telling that it's true. I'm telling that these are possible sources of advantage. Then you have to see if you are able to extract that information from the system. But this is the truth. You have, if you have n qubits, you will have 2 to the n elements of your state that you can use to encode information. And then another feature that was very interesting is the possibility to use also what are called these NIS devices. So what are these? These are noisy intermediate scale quantum devices. So you know there is a lot of effort for building quantum computers, but actually there are many challenges. And one of them is that these are very prone to decoherence, so these are very noisy. And the other thing is that up to now the system have a number of units that is still limited. Okay, so this is the reason for which Presky a few years ago actually labeled this category like this epoch in which we are, these times in which we are, in which there is this category of devices we were called Minsky devices. And after the first proposal of Fujii Nakajima, there were actually proposals in many systems. Okay, I have a reservoir done with trapped ions. I can have a reservoir done with optical light modes, or with NMR, with molecules, with lattices of boson of fermions, or even with the quantum circuits of quantum computers. So there were many proposals, theoretical proposals. Okay, and up to now, so now 2 years have passed, and actually the experimental realization is still in its infancy, so there are many challenges. So actually the first things that came out, they were speaking about quantum reserve computing, but actually many of them didn't have any memory. So they were actually operating as a stream learning machine. And these were implemented in atoms, in these circuits, in photonics, and so superconducting circuits, in photonics, and settings also with superconducting qubits. More recently, there have been effort in trying to go forward and try to really have some memory into the system. And if I have time, I will say something about the experimental work to Valentina Parigi at the end. And then there is another theoretical proposal of Philip Walter, was first attempt also for experimental implementation with quantum memory stores are available in the art. So quantum experiments are still in its infancy, but there is a strong interest actually in going into that direction to see if it's also something that is possible. And what I would like to give you here is just a flavor of different examples in which I've been working of reserve computing, just to show you how the physics of complex systems can enter into this kind of problems. So the first proposal I was telling was this proposal of Fujii Nakajima. So what did they have? They have a transversism model, so they have qubits. So this would be the X Pauli matrices at sites I and J. And here there is a random coupling between them. And then there is a transverse field in the Z direction. Okay? So they were considering this system as a reservoir that was good enough to spread information. Which information? The information is actually injected in one qubit. So this is one qubit, is coupled with all the others, but at each time in which an input is sent, the input actually is used to reset the state of that qubit. So if this is qubit 1, it will be at some state that depends on an input, where the input at time k is encoded just in the superposition between 0 and 1. Okay, so this is the mechanism of encoding, and then at each time steps, what you actually have is a unitary dynamics of all these qubits coupled with all the others, and then at the following steps, the qubits is rewritten. Okay, so you rewrite row 1, and I don't know how much you work in quantum and you all remember definition of partial traces and so on, but if not, everyone knows about marginals of probability. So this would be just the marginal of all the probability, quantum probability related to these qubits. And this is the qubits that you are rewriting at each time step. So you write the state, you couple with the other, you write the state again, you recouple with the other. And every time that you rewrite the state, you are actually erasing some information. It's the information on the correlation of these qubits with all the other qubits. Okay? So this is the map that was considered. And what is the output layer? So the output layer, you have this system that is evolving, and the output layer are just the expectation values of the qubits. You can take expectation values of qubits individually, you can take correlations, you can build up to 2 to the n actually of observables that you can use independently. Okay? So the main thing about it is that actually you do not need to tune this system. So even if your system is not so big, is noisy, and in particular you do not even know exactly which is the value of the coupling Jij, it doesn't really matter. You have a system and you use it like, let's say, a black box to see if it's able to induce sufficient scrambling on the information to do the task you want. Okay, and then this was an example of the task. One of the tasks. There are many tasks in the paper, and one of that is this timer task, and it's just a way to show that the system has memory. A timer task is a task in which you say, okay, at some point I will send the input will change from 0 to 1 in the system, and I want the system, the reservoir, to be able to output at, at some delay, for instance, a delay 10, when this was happening. So when there was a change, just a time. Okay, so easy to see that you understand my explanation. So the task for the system is I interrogate you at each time, and I want to know when 10 time steps have passed from the change in the input. Can you do this if you do not have any memory? Of course you can't. So this is a trivial task, but this is a task that you can do only if the system is storing memory, because the system has to remember that 10 steps before there was a change in input. So this is a simple test for the memory, and what they were showing actually was that depending on the size of the system, the memory was going, for larger sizes there was more memory and this kind of things. So this is an example of task, just to show that this kind of system can have memory. And then after this initial work, there were, as I was telling before, many attempts to study different systems. And one can ask, okay, but if any system in which you have a dynamics that is not completely oblivious of the past would serve to do reserve computing. And these are actually the properties that you need to fulfill to have a universal reserve computing. So you need to have convergence or equal state property. This means that actually your reservoir is working like a black box of processing unit for your inputs, forgetting about its own initial state. So for instance, in the case of the Ising model, you want that the initial state of the full Ising model at some point is forgotten. And you just keep on processing the inputs, forgetting these initial states. Okay? So this is called equal state property. And then you have the fading memory. You want the system to be able to record the past, but not all of it. Because if not, I mean, you have a finite amount of system, so you need a fading memory mechanism. And then you want to add separability, that is the ability of the system to distinguish between different inputs. Even if you have all these three properties and you can guarantee that your reservoir is universal, this does not tell you how good it will be in a specific task. Okay, so this is a different. Okay, so the thing is that when we started to do reservoir computing, that was like 5 years ago, we started to play with this model. And what we actually seen is that the performance was changing a lot from one regime to another. And it actually turns out that this system, of course, has a very rich dynamics, and in particular, depending on the degree of disorder that you have in this system, you can have a transition between a regime in which you have that locally the observable of the system are in kind of thermal states, and another regime in which you have localization in which this doesn't happen. And this was already proven experimentally. This is an experiment in which you have ions in a trap, and depending on the disorder that you have in the ion traps, you can have the ions during time thermalizes locally, or you can have the ions remain in a state that is pretty similar to the initial one, and then you have localization. So actually what was happening in the system when we were playing around is that we were moving from one regime to the other. And for us, it was a little bit less trivial because we were actually not playing around with the parameters. We were only changing the time lengths in which the system was operating, but this was enough to go in different regimes. And to make this short, what we found is that actually you can identify, depending on the strength of disorder here and the average field that you have here, you can actually have different regimes in your system. So depending on this H and W, that are the degrees of disorder, and which is the homogeneous field strength in the Z direction, you can actually have parameter regions in which you have something that is similar, that is this thermal phase, and other regions in which you have a localized phase. And the operation of the system is pretty related to the phase that you have in your system. And actually the reservoir computing is able to operate in this thermal phase in which you have a fluid let's say, spread of information, but it doesn't work at all in the many-body localized phase where you have actually pretty stiff dynamics, something that is actually also intuiting this kind of maps. And here are just example of tasks that show this. So this is the information processing capacity that is a task, like, let's call it a super task, is a task that is evaluating the memory and the nonlinearity that you have in your system. And what is actually fine is that it is very high in the thermal phase. So now I'm cutting this diagram in this direction. So this is thermal phase and this is localized phase. And you actually say that in the localized phase, the performance go down. And there is actually also something interesting that depending on the task, you can actually have also here at the transition, you can actually have a peak at the transition between the two regimes. And this is something that is happening in some of the linear tasks. So after this, so the first example is an example in which the ergodic dynamics is shown to be good for server computing and more efficient for information spread, while localization freezes the dynamics and is not good for it. And looking now at a different example, we wanted to see if it was really the phase, the important thing, or and if this could be actually detached from other feature of the system. So in this system, there was disorder. What happens if you have a system that is completely uniform? So we started to play with this Gaussian model. So in this Gaussian model, we have a lattice. You see now there are two adjacent bosons are coupled with a constant coupling, and then you have a repulsive interaction term. And in this kind of systems, it is known that you have, in the fundamental, in the ground state, you have two phases. One is an insulator phase in which you have a boson on each side, very well organized, and then you have another phase that is superfluid in which the state is spread into the system. Now, it was shown in a paper that triggered our attention that actually when you go in from one phase to the other, and you go from one to the other depending on the ratio between the local coupling and coupling in the Newtonian, you actually in the middle have a phase that is actually ergodic. And we wanted to know if that phase was good to do reserve computing, if you could observe the equals to that. So this would have answered two things. One is if ergodic dynamics is better to do reserve computing, and the other is if whether disorder is really necessary, because actually this system doesn't have any disorder at all. And the short answer is that actually the disorder is not really necessary. The dynamical phase of the system is what is playing the major part, and the different tasks is actually able to identify the best regime of operation in the thermal phases, but not all of them. Actually, in some of the phases, also the superfluid phase was working pretty well. So these are two examples of tasks. This is a nonlinear task that requires quite a lot of linear memory, and this instead is the parity check. So it's looking if you have input 0, 1, is looking at the parity of inputs that you have received in the past up to some delay. And this task actually was performed well also in the superfluid region. So there is, let's say, an interplay always between, so the main thing seems to be the dynamical phase of the system you have. It doesn't really matter if you achieve this dynamical phase through disorder or not, but there are some features that are important, and the spread of information is crucial. And that will not boring you, but this can be shown to be related to the fractal dimension, that is the spread of the eigenvectors of the system. So it will actually be traced back to that feature, the fact that you have this label. So this was a second example. Disorder is not always needed. This could be a take-home message. And then up to now, and also in the literature, there was a lot of interest in studying different system in which the difference was actually influencing the unitary dynamics, so different Newtonians. But actually, reserve computing is not only about the unitary part. I was telling you need to have a fading memory mechanism. Typically, the fading memory mechanism is because you have a dynamics that is actually of a system that is interacting with an environment. And in the first example I was showing before this interaction was done with an erase and write map. And overall, it is also known, so just to make the point, The fact that you have need of having a fading memory would tell you that you need some dissipation and tolerance. And this was actually what was already included in this Fuji-Nakajima map because there was the erasing of information. So you need this, okay? But on the other hand, you also imagine that if you have something that is dissipating information, you lose expressivity. So here you have to find which is the good point of operation. So the coherence can be positive or negative. You need to see how these things balance. And actually, in work with Anna Palacios, we were looking at this. This was a TFM at the institute, and we were actually looking at this information processing capacity, um, how this would change under the action of the coherence, and we were actually finding that this was in general detrimental because coherences are crucial for the well the cyber computing. Even say that, okay, you need some decoherence, but which is the best way to do the coherence? So let's look not only at the unitary part, let's look also at the dissipative channel that we are in. And what we actually find is that having continuous dissipation, even in master equation formally, so Markovian dissipation, is actually better than having a and bright map. So this was the work of Antonio Samia that is doing the PhD, and he was actually showing, so all the red curves are performances of this reservoir computing when you have a map like in Fuji Nakajima, so you erase and bright at each time stamp, so it's discontinuous erasure of information, or a map in which you have a continuous dissipation, like normal dissipative systems that you always use, in which you have some gamma damping in your system and you have your dissipation acting continuously. And what it was found is actually this continuous dissipation was able to achieve better performance than discrete one in all the tasks. So here the best performance of course is being in one, and this is the performance as a function of delay. So performance, for instance, this is the short-term memory, the ability to remember fast random inputs between 0 and 1. This is the Narma task I was showing before, and this is the parity check. So again, not only the unitary is important, also dissipation here, and this just to do a task that is more fancy. This is forecasting of a chaotic time series. This is Maki glass. So you can use this system also to do forecasting. You inject a chaotic sequence and you want to know up to when the system is able to predict the future behavior of the chaotic series. And also in this case, the continuous dissipation will work in. And as a note, there is a lot of interest in the quantum community on non-Markovianity. The Markovianity arises when you have a map that is actually not visible in a good sense, and it can actually be shown that no Markovianity can be a resource, also in this case. Even if it's a resource that cannot be really cannot be separated by the world way in which the system works. So it is actually difficult to find a one-to-one correspondence with no Markovianity being a good resource for all memory tasks. It's not so easy. But you can do it in a synthetic example, and this could be a synthetic example in which you do a non-Markovian evolution, in which you have actually that you take a convex combination of states of the system at a present time and the previous time. So for instance, this would be a perfect non-Markovian evolution to have memory at the time step given by this delay. So if tau A here is 10, then you will have a very good memory, of course. Okay, so you can do a synthetic example to see that of course non-Markovianity can be resources. Another thing is that you can do, for instance, the Maki glass forecasting and you can have a better performance. This does not necessarily happen. So this was the last example, and then we have time to speak a little bit about continuous monitoring. Yes. Yes. Okay. Short anyway. So there is a major problem you can imagine. In a quantum systems are very good, but then when you touch them, it's a problem. And then you need to touch them because you want to extract information. If not, the whole thing about reserve computing is about extracting information, and you need to do measurement. And this is particularly painful in reserve computing because I was telling from the beginning, this is an online machine learning approach. So you need to measure and then continue the dynamics, measure again, continue the dynamics, and every time that you measure, you highly perturb the system. You have the collapse of the function, and then this is a limiting factor. So what we proposed a while ago was to consider that instead of having your quantum system in which you do what are called as projective measures that are extremely destructive, you could take an approach that was a little less invasive, that is called weak measurement. And what is weak measurement in a few words is that if you have a system A you want to measure, you can measure this system with a projective measure, and this would be extremely good. For instance, if you measure if you want to have your spin up or down, like after the measurement, even if before it was in a superposition, at the end of the measurement, of the projective measurement, you will be up or down, so you have destroyed all the superposition, okay? But you can do a weak measurement. What do? You take this qubit, you couple it with another qubit, and then you project the second one. So this is an indirect measurement of the first one, and the effect is weaker, okay? And this was generalized in the proper way. This was seen as a good strategy to do reserve computing. So you could do reserve computing actually doing this weak measurement. And now let's take just a brief look to this just to have an idea. Here, if you have a real trajectory of the system when it's not measured, and this could be you have input injections, and then you may measure another qubits, and the other qubits will move around because there is a driving, okay? And then you have these dynamics. So this is the ideal dynamics. If you do the quantum measurements, actually what you have is that you are taking the system completely out from the natural dynamics field. But if you do a weak measurement, you actually end up in a situation like this. So weak measurement can be actually quite good for this. So we propose to do reserve computing with discontinuous monitoring and weak measurement. And which would be the alternative? If you have a quantum system and you do not want to do this weak measurement, so if you do projective, you destroy all of it. So you can do projective, and then you say, okay, now I restart again. And I just follow up a little bit more, one step more. And this is a restarting protocol. And I'm smart enough. I do not start the dynamics from the very beginning. I start the dynamic from temporal window that is so the idea of these two strategies, and you can compare what is the resources. In the weak measurement, the measurement is less informative, so you need to do more measurements, and here you need to rewind the dynamics and to repeat it. So you can analyze this in terms of resources, and these are two valid approaches. So we compare them, and to make this short, this long story short, this can actually work, and also in terms of resources, it can be actually very convenient, depending on the length of the fading memory, that is the length of the time you need to restart the simulation. And then what we did was to propose this in photonics, because in photonics is pretty good, because you can have part of the light that remains into a cavity, and is your reservoir, and part of the light instead that you extract from it and you measure it. So part of the light, you can have a beam splitter, a simple beam splitter can split the light in a signal that you measure, and the other part of the light remains in the system retaining memory. So this was extremely good. We have been studying how it works and whatever, but actually for experimental implementation it was very hard. And then we started to work at this with Valentino Parigi at Sorbonne University at the Laboratoire Castle Bruxelles. And actually what we did now, and this was posted in the archive a couple of months ago, was not to feed back information like here coherently. So here you have a quantum optical signal, and this continually circulating in this cavity. There were other details I'm not telling here, but this was the main idea. Here instead what we did was measuring the signal at the output and to re-inject classical information about it inside the cavity. So there is a classical feedback, because it was too hard to do the quantum feedback at this very first level. But this was shown to be enough to setting, of course, some memory into the system, and this is a very promising first step to continue in quantum mechanics. So this is my last, not too short slide, and is about not a summary of things I said, but just a vision of the field. So there are many opportunities in quantum reserve computing. There are all the opportunity of classical reserve computing that I was mentioning in the beginning, plus the possibility to have efficient fast processing, for instance, in photonics, but in a system with an exponential number of degrees of freedom. So you have the possibility to implement these also in devices that are not completely controllable in quantum settings. This is another advantage, another opportunity. And important, you can do quantum tasks. So the task I was showing before was you were injecting a classical input in a superposition state. But actually, you could actually consider that the quantum state of the qubits, for instance, in that setting, that was the quantum state that you wanted to process. So that would be an input processing, quantum input processing, okay? So this is something that is powerful, because if you want to do the same thing using classical reserve computing, before you need to do full tomography of the quantum states, and this is again something that is very consuming. Then you can do distributed quantum machine learning using entanglement between units, and we also start to study this, and we don't time to speak about everything. And this is the work, so I put it in the image. So in this work we did two things. One is to show that you can do distributed quantum mechanical computing, and the other is do it with a mechanism that is called measurement induced computation. So actually the input was injected there, but it's a bit technical. So this is suited for distributed machine learning. And the other thing that I think can be fun for physicists is that actually this shed a new light on many body system. For instance, when we realized that this fractal dimension in the Bose-Hubbard model was useful for describing the cell computing, this was interesting for that community because they have a lot of indicator and study of these quantum chaotic systems, and they see that they have the things that they actually find have an impact in the way in which information is processed by the system is a new way to look at them. And also we are looking at metastable quantum systems. There are many things that can be studied. Challenges. Mainly, the main challenge is the measurement. So the fact that when you measure, you have back action effects, you have statistical noise. And other question, I was telling at the beginning, you have an exponential number. Sorry, the more difficult is to have a meaningful signal to noise ratio of the stuff that you are trying to extract. And this is a problem related to concentration. And then there is still the issue to define which are the quantum resources that are really needed to that. In the work with Anna, we actually found, for instance, that entanglement by itself was not really the main crucial quantity given the good performance. The good thing was coherence, but entanglement not so much. So there is still the question about which is the quantum advantage at the very fundamental computational point of view level. And then there is the open challenge of experimental implementation. And then, of course, the bar for applications is pretty high. To become competitive with that is also another challenge. So I thank you for your attention, and hope it was okay.
Thank you, Roberto, for the talk. We do have a few minutes for questions. Yes.
I'm wondering about the non-Markovian extensions. Is it possible, actually, like with classical systems, to extend the phase state of phase space of the system to map non-Markovian dynamics onto Markovian, but with at the expense of increasing the number of variables? Well, usually you, for instance, can go from second order equation in classical system, you can go to coupled to second orders. And so you just expand the number of variables you need to describe your system, but then you gain in reducing it to Markovian picture again. Is it possible with quantum analogs of non?
Sorry, as far as I know, it's not always the case. So the non-Markovianity definition in quantum system is that you have you lose divisibility of the map. So if a map is Markovian and you go from one time to the other, if you split it in two intermediate maps, in an intermediate time, the one that you have in the middle, let's say, are not well defined like the global one. So this is not something that you can always solve going into a larger space. So the connection, as far as I know, is not immediate. But I also have to say that the fields of non-Markovianity in quantum system is one of the most controversial I've ever seen. I've seen people fighting just for use of the word, of the definition. There have been many measures of non-Markovianity introduced. So here we try to take a very simple approach, just telling one thing that everyone agrees about is that if you have a channel that is Markovian, a non-Markovian one is more general in some form. Now, with respect to the thing that you are telling, you can extend the system. I mean, this is also a way, but for instance, in our system, you could think, okay, I can monitor a part of it. And this will be always be non-Markovian in a sense, because it will depend on the external degrees of freedom. So that kind of non-Markovianity that will always be. But we try with the people at the institute to do a numerical study to see if this was a good approach to see an improvement in the performance, and it didn't work. It's too complex. If you have, for instance, n-coupled oscillators, and you say, okay, half of them are the reservoir, and the rest I just traced out, it depends a lot on the form of the couplings and everything, which is the resulting performance of the sub-system. And we didn't find any conclusive results. And this was related to what I was telling before. You can have non-Markovianity, and non-Markovianity by itself, I mean, it's not temperature. Non-Markovianity is a feature that is related also to other things, and there are many measures in this quantum system. So we didn't find any monotonic relations of the performance of tasks with non-Markovianity. It's too complex.
Any more questions? We should give another round of applause for the speaker.
Then our speaker is handling. So we are ready for a talk by Han Lim Sun from the Nordita Institute, and he's gonna talk to us about unveiling the importance of non-shorted paths in quantum networks.
Thank you for the kind introduction. I'm Hallin. I'm from Nordita, Nordic Institute for Theoretical Physics in Stockholm. And this is actually the first time I present this work that I slightly moved to the quantum network regime. It's a collaboration with Xinqi, Gaogao, Kim, and Tim Fang, and Hao, Shlomo, Renaud, and Xiangyi, and also Jens. So I'm going to talk about quantum networks and quantum percolation. So first, I would like to introduce notation. What is quantum network in the sense that it could mean many different things. So in this network, the goal is trying to understand entanglement transmission in distance, in the sense that, for example, in quantum communication, the entanglement is a very useful resource for such communication. So we want to understand how two nodes in distance can be entangled in a certain protocol. So in this quantum network, we introduce nodes as qubits, and links are the partially entangled state shared between these two qubits. So here we just take the simple form, and we introduce this parameter theta between 0 and pi over 4 serves as a link weight quantifying the degree of entanglement. If theta equals 0, there's no entanglement. If theta equals to pi over 4, it's a maximum entangled state. So the basic question we want to ask is that how to transmit entanglement between two distant nodes in a network setting. In other words, how can we entangle two distant nodes under some operation allowed, basically local operation you can do on each node. So traditionally, there's something had been discussed decades ago called singlet conversion protocol and related classic entanglement percolation. So the idea is quite straightforward. They said that every link, this shared entanglement state, can be converted to a maximally entangled state with a certain probability p, and this p is related to parameter theta. P equals to 2 sine squared theta, and otherwise no entanglement left. So basically, with a partially entangled path of entangled link, you can like gamble with the probability to convert it to maximum entangled, or you lose it completely. So in this way, the problem of connecting two distant nodes is converted to a simple bound percolation problem that you establish links between two nodes with probability p. And then, after converted to a percolation problem, of course, you can find this percolation threshold PC, or if you use parameter theta, it will be theta c. So the theta c is a threshold for establishing a sufficient entanglement that allows two infinitely distant nodes being entangled. So, but the problem here is that to achieve entanglement transmission, because you draw link with probability p, and if you put a link, it means maximally entangled. So to achieve such transmission, you need to have at least one path of maximally entangled state. So called singlet. So you need to have a path of singlet that's connecting these two nodes farther. So wondering if there's other possible scheme to relax this requirement. The idea is that if you have two distant nodes, and you might have a lot of paths in the middle, long, and the paths are formed by partially entangled links, but there might be many of them. So can we find a way to take advantage of the redundant but imperfectly entangled path? So based on this thought, proposed called concurrence percolation theory in this paper by Xiang Yu in 2021. So the idea is that now we just want to directly calculate the concurrence between two distant nodes, where the concurrence describes the entanglement. So, which is this concurrence parameter c is also a function of theta, c equals to sine 2 theta. And when c equals 1, these two distant nodes are maximally entangled. So we just find a slightly different way. We do not require all the links being the perfect entangled links, but we just think of and what is the concurrence between them. And we might have other protocols to achieve maybe all the intermediate links are not perfectly entangled, but the concurrence between the starting node and the end node equals to 1. If this is possible, then basically we achieve the goal of entangled perfectly to remote distance, possibly with less resource, because we relax the requirement on this perfectly entangled path. So I'll go into the details of this in a few minutes. So I want to talk about the percolation theory. And traditionally, in complex network or random network theory, the percolation is actually the order parameter. Usually, we consider a cluster-based measure. For example, the most commonly other parameter we use in calculation is the relative size of a giant component, or equivalently, in most cases, equivalently, the probability of finding a node in the infinite connected cluster, P infinity. But if you look back on the early stage of percolation, for example, when people studied the percolation of lattices, a slightly different notation is used, is based on path. Basically, where lattice from the traditional way of thinking of percolation, you need to have at least one path connecting the two faraway borders so that water can flow through the material. So another notation is called, in this paper, called sponge crossing probability, which is that what is the probability that there is a path connecting two faraway boundary nodes. And people use, in network science, use this cluster-based measures because it is more convenient. But they're related in such a way. For example, if we simply draw axis of P, the probability of retaining a link in a percolation setting, then you have a critical threshold PC. Below the PC, you have a finite cluster, and the order parameter are the size of the giant component is equal to 0. And above the threshold, you have the R greater than 0, so describe the percolation position. But if you use this path-based measure, this probability as order parameter in some sense, then within the subcritical regime, you do not have such a path connecting to boundary node, so the water cannot flow through the material. So PSC equals 0. And at the critical threshold and above the critical threshold, you will have an open path between the two boundaries, so water can flow through. So if you look at this quantity P at C, then below the threshold, P at C equals to 0, and above or at the threshold, P at C equals to 1. So we were looking at this quantity, and the reason we are looking at this path-based measure is that when later I introduce the concurrence calculation, you will see that there's no cluster-based notation on that model. So next step, I want to show how we can actually calculate the probability of connecting two boundary, at least, let's say, two far apart nodes. And here, we discuss a simple scenario, which is called series and parallel network. So you can consider a network formed by resistors, and you want to calculate the effective resistance of the whole network. And in a simple case, you can simply apply the series rules and parallel rules to two resistors in serial, and the effective resistance is the product resistor. And if you put two resistors in parallel, then you can right? So imagine that the whole network, if you want to calculate the probability of connecting one node to another parallel, and in series parallel network, all these paths are formed by serial rules or parallel rules. So in this way, you can basically replace all the middle links with one link, like the case of the resistance. So we can consider the series rules. For example, on the right side, if you have two nodes, A and B, connected via an intermediate node, and the probability of A connected to the middle one is P1, and the probability of the middle one connected to B is P2, then clearly the probability of A connecting to B is simply equal to P1 times P2. This is a series rule. And you can have a parallel rule in the sense that if there are two different paths connecting node A and B, then the probability of A and B being connected is that these two nodes are connected by at least one path, which is simply given by 1 minus P1 times 1 minus P2. And P1 and P2 is simply the probability that these paths exist. Again, so this rule can only apply on the simple serial parallel network. For example, in that case, if you want to calculate the probability of A and B being connected, we can first use the series rules to calculate the probability of the path below exist and the probability of the paths above exist, and then replace all the links in the middle. But of course, there are some other cases. For example, this you cannot use simply use the serial and parallel rules to replace. There are some other rules that, for example, the star mesh transformation can help you approximately calculate the probability of A and B being connected. Okay, so this is about how we calculate the Spong crossing probability. And using a very similar notation, we can think of the Spong crossing concurrence, which is the concurrence between two far apart boundary points. Just like a counterpart of the TX between two sequences. And really, now you do not have a cluster-based method because you do not actually calculate looking at the probability of connected, but a different measure of concurrence exists on the path. So you don't have a naturally defined cluster size. And we can assume a similar situation, not necessarily, but possible situation where there's a threshold C, threshold for concurrence C, in the sense that below the threshold, the concurrence between two faraway nodes are zero. And beyond the threshold, the concurrence equals to 1. So just like a equation. And the difference here is actually that if you do the calculated concurrence, different series rules and parallels rules apply. For example, if you want to calculate the concurrence between A and B are connected in serial, then you use the same C to C1 times C2. But if they are connected in parallel, use certain protocol, you can achieve this result, which is the concurrence between A and B are formed by the concurrence of the single separate path, C1, C2, in such a way. So now you can see the two models are very similar, just the rules of calculating the concurrence or the probability. So they reported in their 2021 KRL paper that they studied this model on lattices, back lattice, square lattice, all these structures. And the observation is that the critical threshold, if you use the theta as a control parameter, basically, the theta for quantum propagation is always smaller than the classic entanglement propagation. So meaning that with a smaller level of entanglement, you can actually achieve that two faraway nodes are perfectly entangled with concurrence equals to 1. This is the first observation. So it means that under this concurrence propagation framework, it's possible to propose a more efficient strategy to entangle the faraway nodes. The problem is that why this theta is always smaller for concurrence propagation than classic propagation. So this is a paper I was involved in. The previous slides are just background information, basically. We want to understand why the threshold for quantum propagation or concurrence propagation is always smaller. So we consider this concurrence propagation model on a specific network structure called UV flower. So the UV flower is defined iteratively. It has a self-similar structure. The way of defining this UV flower is just by replacing every link, use a motif of UV flower. And UV flower is simply this motif. You have two nodes, A and B, and they are connected by two different paths. One with length U and the other one with length B, and U is the smaller one. For example, this is the 2, 3 flower. A and B are connected by a path of length 2 and a path of length 3. This is a basic motif, and at every iteration, you replace the link in this motif, use this motif itself. So you get to that, and you can continue. So the reason why we study this structure is that, first of all, it is a perfect serial and parallel network. Just like the example I was giving before, the A and B are connected by these two paths in step 1, and then it's connected by a lot of paths, but you can apply series and parallel rules to replace the whole structure in the middle using one node. Using one link. So we can exactly apply these rules with no approximation. And the second thing is that it allows us to calculate this crossing probability and concurrence via RG renormalization group method, because the structure itself is defined in such an iterative way. It has a self-similar, so if you zoom in and you zoom out, the structure is also the same. And the third advantage is that you can analytically control the path length that's connecting to faraway nodes, because in that case, you can actually list how many paths between A and B has length 1, how many of them has length 2, how many of them has length 3. It's just controlled by this parameter U and V. So this is the basic RG method, how we calculate this probability. So using the series and parallel rules, in the motif, the nodes are connected with probability P, and after one iteration, you can replace the motif using one link. The probability here is RP. And RP can be simply calculated using the serial and parallel rules. So you calculate the probability of that path, upper path, connected. So notation I use here is series and PPP. You have U path, and the probability of making that serial path to one single edge serial. That first part. And then the lower link is obtained in the second part. And then you put two paths together using the parallel rules. So this is a very simple case. The RP, you can write it down explicitly like that. And of course, next step, you can do this operation again and again. In the end, you will shrink the whole network with one link. So the probability of these two end nodes A and B being connected is just by recursively apply the function R on a probability B. So if you want to obtain a non-trivial probability, non-zero probability PSE, you can simply study the fixed point equation of P equals RP. You want to find the stable fixed point. So this is a rather simple, because of the self-similar structure, and you can perfectly apply the zero parallel rule. You can calculate this exactly and analytically. And the same story for the calculation of concurrence between these two nodes. You can apply the same zero parallel rule, just the details of the rules are different. And of course, you can obtain the concurrence between these two faraway nodes by iteratively applying function again and again. And the same thing that this threshold can be obtained by say fixed point equation. So here I'm just showing one explicit example. If we do it on the 2-2 flower, this is the basic motif, and then we can calculate the critical concurrence of critical probability, and you can of course express it in terms of theta. And indeed, for the concurrence calculation, the theta is smaller, 0.549 times pi over 4, and the other one is 0.75. Just recall that the probability P, concurrence C, are connected with the theta such a way. Okay, so this is just an example, and we'll show some more general results. So here is the limit of B goes to infinity. In the UV flower, the long path goes to infinity, and we can do asymptotic analysis on this critical threshold. So here is the result. So when V goes to infinity, you can imagine that this whole structure is facing a T. So the percolation threshold, the P or C, should approach to 1, because it is but how fast it approaches 1, it makes a difference. For example, here, we do the asymptotic analysis, P threshold equals 1 minus this ln U over U minus 1 times V to power minus 1. And V to power minus 1 is just a common factor here. If you see the difference in the free factor, 1 is related to the shortest path U, and the other is not. So by directly looking at this equation, you could indicate that in the first classic bound percolation, the shortest path play a role in this scenario, but the concurrence percolation, the shortest path, do not actually play a role. And we can look at this equations more clearly. So I have the long path of length v, and here every link would exist with probability pth. So the whole path of length v exists with probability pth over 2 power v. And because v is going to infinity, so it equals to u over u minus 1, which is a constant. This meaning that at the percolation threshold, you have a non-zero probability of finding a path of length v. But in the other case, is that the concurrence along this long path v is like e to the power minus 1/4, which means when v goes to infinity, this quantity goes to infinity as well. So what can we say about this? So we can conclude this in this way. At criticality, when the network collapses, all long paths in concurrence population are exhausted. Because at the threshold, the concurrence along the long path equal to 0. You have to run out all the resource before. But in the classic population scenario, the long path remains with a constant probability, which is u over u minus 1. But the network collapse simply because the long paths are not strong enough. In the quantum calculation, it's because the long paths do not exist anymore. So from here, we can go to this conclusion that the long paths play a more important role, or stronger role, in concurrence calculation than classic calculation. The long paths try to maintain the connectivity of calculation or concurrence calculation stronger than the classical counterpart. And so in the last bit, we tried. So previous example was simply on the UV flower area-specific structure, and here we want to do something slightly more general. So we consider the example of real-world network. To start with, we consider the path decomposition, because you can imagine it's impossible to count all possible paths between two nodes in a random network. But we can sample some paths. So I'm not going into too much details here. But the idea is that, let me go here. The idea is that, so this is internet topology. I don't remember exactly the data, the meaning of it, but this is just as an example, we show some real network structure. We find two nodes, and we sample an overlapping path between A and B. So we have some short ones, we have some longer ones. And we want to study how the long ones and the short ones contribute differently to the connectivity. So we consider the rerouting and detour. For example, we can pick a path of length v, and we make some detours to make it longer. And just very quickly, I show you this result. So we use this ax cubed, this x can equal to c or p, representing the classic concurrence population. This quantity basically captured how resilience of this parameter against approaching to the trivial threshold when the long path becomes very, very long. Because when the long path becomes infinity long, the threshold will always give to the trivial one, which is theta equals pi over 4. The ax captures how strong the resistance is to approach this trivial threshold. So the idea is that if this function axq increases faster, means the stronger resistance. And so you can see that in the real internet topology, the same results apply as well. The quantum case is more resilient against the longer path in the network. So just quickly go to the conclusion. So here, in this work, we reviewed that the non-shortest path play a crucial role in enhancing the connectivity. And there's something I did not have the time to show, but we can also study the critical exponent on these two models, and they are very different. So the concurrence percolation is not a very small modification of the classic percolation, but like statistical framework is completely different in modality class. And the conclusion is that basically we can achieve entanglement transmission via longer but weaker power, caused by partially entanglement rings, if such paths are sufficiently redundant. Thank you very much.
Anyone has any questions?
In the mechanism, you have this mechanism, and you add on the top of this, that I understand is a unitary mechanism, also local or global dissipation channels. Can you say something that everything? Okay.
Okay, thank you. Then I think we are just in time, unless there are maybe one short question. Then we thank Han Ling again.
So can you hear me? So first of all, I would like to thank the organizers for this very nice seminar and for the opportunity for me to be here and present our results. The title is Complexity of Iterated Quantum Protocols, but actually the main part will be that I will try to convince you that even a single qubit in some protocols can be can have a very rich dynamics, and it can be really complex. I hope I can convince you at least to some extent. So this work, this idea behind this work goes back, I think, more or less 20 years. And so there is a lot of collaboration with different groups. We started this with the group from the Prague Technical University, but also my colleagues from Budapest were involved, many of them, and also a group from Darmstadt and one from China. They were all involved in the work which I will present to you. Okay, so when I became interested in this problem, entanglement distillation was already a thing, and people were interested in that. And maybe you know the idea behind the entanglement distillation. The previous talk was also contained this idea, and it was explained a little bit. So the idea behind entanglement distillation is that you have quantum states like qubits, and they can be in some state which has this entanglement, and you would like to have some highly entangled state, the end of the process. But because they are in remote laboratories, so this one laboratory is far away from the second and far away from the third one, like maybe in some of these networks we heard about. So what you can do is some quantum operation in each local laboratory, some measurement maybe as well, and some classical communication. So these LOCC, local operation, and classical communication um, processes, this cannot increase entanglement. So what can we do? We can have two copies of the original state. Maybe we have some process which generates them with some noise, with some error, and but it generates more than one. So we have two copies, and we can use these two copies to have some local operation, some measurement, some communication, and finally we end up with one copy. And sometimes we discard some copies, sometimes we keep them. But at the end, we have, instead of the two copies, one copy, or maybe zero copy in some cases. But in the case when we have one copy, it's not forbidden to have more entanglement of the single copy than the two copies had, because it's only the average overall entanglement, which has to stay constant. But so this whole process is rather complicated. And it turned out that there is some instability and complexity for entanglement distillation protocols. This is very complicated. So what we do is we cut out the first and the second laboratories, and we started to look at a single qubit, but in a similar process. And at that time, it was maybe a little bit exotic. So why would you do this with a single qubit? But nowadays, with the popularity of quantum computers and the huge interest which we have, it turns out that even the single qubit protocols can have some users, we will see. All right. So this will be a nonlinear evolution of the single qubit. And when we talk about nonlinearity in quantum mechanics, it's a delicate topic, because usually closed systems evolve unitarily, so it's a linear evolution. And even quantum channels described as completely positive maps lead to linear evolution. So there is something which is called quantum chaos, which is within these operations. Usually people refer to this, which means that there is a classically chaotic system, and then you look at the quantum counterpart. But maybe in these systems, a single pure quantum state does not evolve to another single pure quantum state in a nonlinear manner. And that's what we are interested in. And as we will see, this will be there in our protocol. And the people, of course, entertain this idea if there is some fundamental, what would happen if there were some fundamental nonlinearity in quantum mechanics. So there are models for this, and there are some entertaining calculations what would happen if. And for example, it turns out that in the context of quantum information, you could do a lot of things with this nonlinearity. Actually, very hard problems, NP-complete problems, could be solved in polynomial time, which means this will be very useful. Also, a very important task, the discrimination of non-orthogonal states, would be possible easily. And there are some other approaches where people find nonlinear evolution in a quantum system, but it's an effective model. For example, in BEC, so Bose-Einstein condensates of cold atoms, there is a nonlinear equation, the Cross-Pitowski equation, but it's not an exact equation. It's an effective approximation. And people suggested nonlinear quantum walks, for example, in this context, but it turns out that at the point when they would be useful in this first two senses, the effective model breaks down and you go back to the original quantum mechanics limit. And we are also in this paradigm, so we don't want to change the basic rules of quantum mechanics, and we will see that we will have to pay a heavy price for having this nonlinearity. All right, so what is a single qubit? Single qubit is the simplest quantum system with, you can imagine, two-dimensional Hilbert space. Even mathematicians don't even like to call this Hilbert space if it's finite dimensional. And so how can we describe it? So usually you have some A times 0 and B times 1. But actually, if you think a little bit about it, you can take out the A and then you have a B over A. And because of the normalization and because of this overall phase, which doesn't really matter, you end up with one single parameter. And this is a mathematically correct thing. You can do this with other quantum systems, higher dimensional. There the result is not so simple. But for a single qubit, you can safely say that this is a complex number, can be represented with a complex number. Maybe you need the infinity as well, so it's a closed set of complex numbers. Infinity would belong to the 1, and the 0 would belong to the 0 computational resistance. Okay, so if it's a complex number, then you can represent it on a plane of complex numbers, very well. But there is another representation which mathematicians like. This is the Riemann sphere. So instead of the plane, having a map of the globe, the Earth, you can have a map on a sphere by a stereographic projection, and this sphere is called the Riemann sphere. Very convenient representation of the complex number. Convenient because the infinity belongs to one point. And if you look at the quantum state, you can realize that this Riemann sphere is nothing else than the Bloch sphere. Maybe some conventions you have to adjust, but otherwise it's the Bloch sphere of the single qubit. Okay, so the Bloch sphere is the surface, because the Riemann sphere is defined as the surface of this globe. So what is inside? And so there is, in mathematics, there is no natural generalizations for the inside of the Bloch sphere, or the Riemann sphere, sorry. But in our context, we will see that there is a natural generalization, and we will see that interesting things happen inside. Okay, so let's have a look at this very simple operation, which is actually basically a very simple quantum computer. Think about it. It's a CNOT gate. And let's first just do the CNOT gate, and we will see what happens. And following this line of thought with the entanglement distillation, we will have two identical states as an input for our qubit. And okay, so this state is just with our nice notation with the Z. It can be written like this. So you just have two independent states which are the same, described by the same Z. So you have 0, 0 from this term. You have 0, 1 and 1, 0 with one Z as coefficient. And the 1, 1 inherits the Z from both states, so it's Z squared. Okay, you apply the CNOT gate, which means that you exchange the last two terms. Very good. And then you apply a measurement, and you measure the second qubit in the 0 state. So this means that you select those states which are 0 in the second state. And what you end up with is a single qubit, because you discard the measured qubit. It's a single qubit output, and the transformation is nonlinear, because Z is squared. So it's a nonlinear transformation. And how can we easily represent it with this single complex number? We had the Z as a representation, and we have the Z square as the output representation. So it's a function with respect to Z. So it's a function over the complex numbers. Okay, how this very simple function, how does this behave? So if the absolute square is smaller than 1, and you apply it not only once, but you also the idea coming from the quantum state or quantum entanglement distillation, you maybe want to repeat this process to have an even better entangled state. So it's very natural to say that you iterate this process. So you have two processes giving the output, and with the two outputs, you can have again a new process. And in this way, you iterate the process. And what happens if you iterate this function? So the z squared iterated, if the absolute value is smaller than 1, everything will tend to 0. If z absolute value is bigger than 1, everything tends to infinity. So these are fixed points. But there is the unit circle. And the unit circle does not tend anywhere. So if you apply this transformation, everything is squared, so the phase is doubled. So you go around this circle like crazy, and this is actually a chaotic process. You can define the Lyapunov exponent for this is 2 times ln2. It's chaotic dynamics. And this is called the Julia set. And there is a beautiful literature, 100 years old literature in mathematics for this. These are iterative complex functions and their behaviors. And it's called Julia set because 100 years ago there was a mathematician, Gaston Julia, who coined this term. How does this look on the globe, on the Riemann or Bloch sphere? This stereographic projection leads to one hemisphere converging to one pole and the other hemisphere converging to the other pole, and the equator is the dividing circle. Okay, what if we add a very harmless looking single qubit operation after the CMOT? So just a single qubit rotation. And it's enough to have the two parameters, so one angle and this phi, the other angle. So it's a 2-parameter single qubit rotation, and you do the iteration again. What turns out that you can combine these two angles into one complex parameter, and you have a new complex function, which looks not so innocent anymore because it's z squared plus phi over 1 minus phi star, which is the complex conjugation times z squared. So it's a function with one complex parameter coming from the single qubit rotation. How does such a map behave if you do iterations? Well, it's not a circle anymore. So those points which do not converge, the Julia set, form these blue sets, and this can be indeed quite sophisticated structures on the sphere. And this is quite well known. So this book, which I showed here previously by Milnor, this one, Dynamics in One Complex Variable, it's a very good book by the famous mathematician, and you can find a lot of nice theorems, and you can study the properties of these maps for pure states. And so just to summarize what happens with these pure states, you have an ensemble of qubits in a pure state, and all of them in the same state. That was important. We take them pairwise. We apply an entangling 2-qubit operation. So maybe it's not a CMOT, and maybe it's not a single qubit operation anymore. We can allow some generic U operation. And we measure the second qubit and keep A only for the result 0. Then we will have a smaller ensemble in another pure state, which is defined by an F function. And so what is this F function? What we could prove that you can find an F function for any unitary operation. And this will always be a quadratic rational function, and you can determine the coefficients here. And also in the other direction, for each quadratic rational function, you can define a unitary. It's not a one-to-one correspondence, but it's constructive in both ways. And there is also this little theorem that you need exponentially many qubits indeed. This comes from the quantum state discrimination theorem. So in order to discriminate quantum states, you need resources, and translate it to a protocol. You necessarily exponentially you have to downscale your original ensemble to achieve this seemingly useful nonlinear operation. There is no free lunch, so you have to downscale a big ensemble in order to have this seemingly good nonlinear transformation. And one very interesting thing for the pure quantum state, and then I will go to the inside of the block sphere. So one very interesting one is that we know that for these maps, there are some which are very special. And this is named after another mathematician 100 years ago, Samuel Latte. And this type of map is chaotic everywhere. So the Julia set is the whole sphere, which means that all initial qubit states are chaotic in some sense. And this was a question whether we have such a map or not with the C0 and the single qubit transformation, and the answer is yes. And then if this is a Latte map, you can have a nice transformation to a torus, and there the map action of the map is just a multiplication with a number. So it's very easy to see that it's like folding over and over on this torus, and this translates again back to the sphere. So this is an ergodic map. Ergodic in the sense that if you have an initial state and you have any small surrounding of this initial state, you take all points, and then you have a finite number of iterations. And after the finite number of iterations, this any small set around your initial state spreads over the whole sphere without any hole. So everything will be covered by this small initial set after a finite number of iterations. So in this sense, it's ergodic. And this is just to show the absolute value bigger than 1 or smaller than 1 is becoming very involved in chess for many. But I go on because there are more interesting things. Namely, we can ask about this map whether if there is some noise, whether this noise would destroy this property of ergodicity. And in order to study this, we just studied for now only the noise in the initial state. So not process noise, not like noisy gates, that's another story, but only the noise in the initial state. So it's not a pure state anymore. And if it's not a pure state, then we can describe it by a single qubit density matrix. And it is well known that the single qubit density matrix has three parameters, three real parameters instead of one complex. And this will define the interior of the block sphere, these coordinates. And what we find, there is a transformation among these coordinates. It's also quadratic, but all coordinates are involved, so it's not so easy to see what happens. And unfortunately, there is no good book by Milnor here, because this is not a complex function anymore, but it's a three real variable system of equations, and the iteration of this. And so it's not so easy to have mathematically precise theorems about this, but what we find, we can prove that only the completely mixed state is a fixed point. So everything which is a little bit noisy will eventually become the completely mixed state. So it's a little bit boring. But what we also found that there is a quasi-ergodic regime. So if we have only small noise, then in this sense, at least numerically, we could prove that in this sense of a small set of initial states covers the whole sphere. And in an optical experiment, we could do 2 steps of this protocol. I don't show the result because I don't have time for this, but you can look up, and this is not so complicated experiment. Okay, this is another example. Instead of this latte map, we have another a single qubit unitary, this Hadamard transformation. Hadamard transformation is defined by this matrix, and it's good because the 0 becomes the equal superposition of 0 and 1. Also, the 1 becomes the equal superposition. So it's a kind of mixing up in the superposition sense the basis, the computational basis states. And now what we find that there is an intricate fractal. This is the surface of the sphere, the pure states. And the two colors means that there is here only a single attractive two-length cycle. So the asymptotically, the state will jump between these two pure states. One is the 0, and the other one is the superposition. And the color is according whether you reach this after an odd number of iterations or this after an odd number of iterations. And so the border of the two regions is the Julia set, which is a nice fractal. And the question is what happens if we add some initial noise to this system. And for the description, you can again use this density operator formalism, and you can write quite easily these functions. And what you find, this is a cut of the sphere like an apple. So it's a vertical cut. So this is the center of this sphere, and the colors are the convergences. So if you add some little bit of noise, then at least on this cut plane, everything will become pure eventually, also here. But there is a third color, the red, and these states converge to the completely mixed state here as well. And there is a thin line, a border line between the two colors. And what we find that this C1 is an unstable fixed point, and you find that if you start, for example, from this neighborhood, then you are on this path going to this other fixed point, but in an unstable manner. Okay, this is the cut, the vertical cut. What you can also do is you can peel this apple. So, and then you make a stereographic projection of each smaller sphere, like peeling the apple. And so this is the pure state, the surface, and this is a little bit below the surface with some purity, because each surface belongs to a certain noise level, which is characterized by the number of the purity of the state. And so on this surface already you can see some red colors, and if you go deeper and you peel further the apple, what you find is obviously these fractal-like structures completely disappear, but it's not so clear whether there is a fractal still here or not. Visible, not visible. And we did some numerical experiments, and with this box counting method, we could quite safely say that up to a critical purity, the fractal remains there in a small scale, but the dimension is the same, the fractal dimension. And there, at this critical point, it disappears suddenly, and the dimension of the border becomes 1. So it's like a phase transition. Just to motivate why not only this single qubit dynamics is interested from this point of view, I show you this example, which is from an older paper by us, but very nicely demonstrates the idea. So we go back to the quantum entanglement purifications tool now. And so you have now the two distant laboratories, and you have two pairs of qubits as input. But otherwise, you do basically the same. So you do a C0 operation, which is denoted by this notation here, and the Hadamard transformation after that, and the measurement of one of the qubits. So it's basically the same protocol, but applied to pairs of qubits, which are entangled. And if you start from one type of initial state, I don't go into the details, which are superposition of 0, 0, and 1, 1 states only, then you can recover the same fractal, which we could see, but it's colored now with different colors, and because also these colors have different meanings. And so those states which are colored with green become fully entangled, and those which are blue, they are completely separable. I think I actually mixed up the notation, but it doesn't matter. So one color is completely fully entangled, so it's the 0, 0 plus 1, 1, which is a very nice Bass state, which is a maximally entangled state. But the other color is separable. Actually, it's an oscillation between two separable states, very uninteresting for distillation. And all this happens on these fractal islands, which are infinitely small-scale islands. So it becomes non-trivial from the point of view of quantum state distillation. So one has to be a little bit careful with quantum state or quantum entanglement distillation, because it might become a chaotic protocol. Okay. So if you are interested in this phase transition, there will be a poster tomorrow by my colleague Attila Portik, and there will be more details and more general protocols as well. And as an outlook, I would like to say a few words about why this can be useful. So one thing is these seem to be a candidate for benchmarking quantum computers, these nonlinear protocols, because they're conceptually simple, and they grasp some properties of the quantum computers. It's not so clear whether they are really good as benchmark more, or maybe like testing a quantum computer. It's almost the same, not exactly the same. So like you run such a protocol and you can say something about coherent and incoherent errors. Then Celtic evolution of entanglement, I talked about it, but if you go to the non-Celtic regime, you can find a new distillation and concentration protocols, and this is valid both for Bell pairs. This is on the archive, it's a new thing, and also G8Z state. There is one publication and the other is on the archive as well. So you can use this idea and this a little bit more refined understanding of these protocols and create a new entanglement distillation protocols as well. Okay, thank you for your attention.
Okay, thank you for the talk. We have time for one question, maybe two, please.
So, thank you for your talk. It was very interesting for me, at least. So, I have many questions, but maybe you already said, but I would miss. So, what happened when you increase the number of qubits? I mean, this type of fractals or complex behavior in the block sphere still appear, or everything became ergodic? Or this is one question, and the other is in a real computer, quantum computer, you expect to see that behavior, and what are the implications of that?
Yes. So, indeed, we also asked ourselves these questions, both of them. So the answer to the first question, if you just increase the number of qubits, Actually, what you will see is, in some sense, a generic quantum computer, because you have initial states in the same quantum state. In many quantum computers, they start with a zero for all qubits, so then there is a state preparation process. But you can put everything into the very big U then, with the many qubits, and depending on what you want to measure in the end, but if it happens that you want to measure, for example, all of them in the same state, then it's already very similar to our protocol. And in that case, if you use, for example, C knots between all the qubits, like pairwise, and you measure all the output qubits, all but one in the zero, then the remaining qubit will be transformed by not a quadratic, but a higher order equation, function, but this will also be a rational function in the end. But there will be some more on the poster. And what was the other question? Is the what happens on a real quantum computer? And so that goes to this direction. So this was my former colleague András Guyen went to the US, and there he had already access to quite good, at the time, quite good quantum computers in 2020 actually, and he could already at that time try to run something like this. Of course, everything was very blurred, and obviously you cannot go to asymptotics, because for that you would need infinitely many or exponentially many qubits. But you can do one step, two steps, and what we had, this chessboard, yes, this chessboard figures, this is already there for one step, and this is the zero step, but this is one step, this is two steps, and at that time they could see this for sure, but something similar to this. But quantum computers are much better now, but we don't really experiment with this type of dynamics at the moment, but we use another protocol, which I didn't show here, which we believe that might be good for testing and benchmarking, and we run extensively on quantum computers to try to figure out what we can learn about the quantum computer through the behavior of this.
Do you have any more questions? Okay. Then I think we can thank the speaker again. So our next speaker is Carlos Perez from this university, and he's gonna talk about making rare events typically in chaotic maps. Sorry.
Thank you very much. Thank you very much for resisting till the end. And I'm very grateful as well to the organizers for giving me the opportunity of presenting this recent work done in collaboration with two excellent students, one of them here among the audience, Adrián Canella Ortiz, and the other one, Iyari González Cota, and the professor Ricardo Gutiérrez from the University Carlos III de Madrid. And the results I will show you here have been recently published in two papers, this one here. And as I was afraid to be a bit out of topic, because I'm going to talk about classical chaotic maps, at least the work chaos has appeared in the previous talk, so we're happy for that. And but there is an open quantum version of what I'm going to explain here in this physical review A, so you can have a look at the general framework I'm going to explain is common to this work and also to the work of stochastic systems that we have also worked on in the last few years. Okay, so chaotic systems. What's the main hallmark of a chaotic systems? It is their extreme sensitivity to perturbations. Even tiny differences in phase space can dramatically result in different time evolutions. Right? So, in fact, the fluctuations in trajectory-dependent observables are just due to the variations in initial conditions. Okay, most of the typical trajectories lead to produce typical values of trajectory-dependent observables, with only a few of them leading to highly improbable outcomes. However, such improbable or unlikely outcomes can be, unfortunately, the most significant because they may have substantial positive or negative impact. Actually, we experienced almost a year ago the consequences of the pouring rains in Valencia. So here are the devastating images. And for that reason, there is a widespread interest in understanding how extreme events arise in chaotic systems and how they can be harnessed in order to ensure that dynamical behaviors remain within acceptable bounds. Okay, and what's the framework to deal with these rare events in chaotic systems? It is the framework of large deviation theory. Large deviation theory deals with those systems whose probability decays exponentially in time. Right? Okay, chaotic systems are deterministic, but they are unpredictable, so they can be just studied in terms of statistical behavior. Okay, and one of the first works addressing the large deviation in chaotic systems was carried out by Julian Taller and Jorge Kurchan in 2007 with this Nature Physics paper, which was called Proving Rare Physical Trajectories with Lyapunov-weighted dynamics. In this nice paper, they studied several chaotic systems. Among them, they studied the standard map. And here, there is the phase space of the standard map for some given parameters. And in blue, they highlighted the highly chaotic trajectory and the very low chaotic trajectory, the integrable trajectories. So in the same phase space, you have coexistence of chaotic trajectories and non-chaotic trajectories. So they were able to study both regimes. So this was one of the first work, and recently it has been extended, the study of rare events, to other trajectory-dependent observables. I shall explain this slide slowly because it is one of the most important ones. So the simplest chaotic maps are the one-dimensional maps. Okay, and we are interested in studying trajectories observables of this kind, right? So I am adding n are the time steps and g is the local observable. So I am adding this observable and dividing by n. So I'm taking the time average of this observable. And I am considering ergodic systems. So the average of this observable is given in the long time by the ensemble average, with rho being the invariant density. Well, I'm interested in not only the average, but the fluctuations of these observables, right? So what's the probability of obtaining a value A very different from that average? And this follows a large deviation principle in the sense that this goes as the exponential of minus n, which is the total number of time steps, times the large deviation function. Okay. This framework was extended, as I said, to other kind of additive observable by Naftali Smith in 2023. Just to be more explicit, let's focus, for instance, in the 10 map. Right? This is the cobweb of the 10 map. And this is a typical trajectory with m being the time steps. Here, the observable I am going to study is the indicator function around this point, which is 2/3. Okay, so I am going to study the fraction of time steps that fall within this blue band. So if I perform many trajectories and I take the histogram, I get something like this, right? So this is the histogram of this observable A by performing many trajectories. And the average value is 0.1, right? Which is twice the width, which is the width of this blue band. Since the invariant density of the 10 map is the uniform distribution. That's why the average value is 0.1. But what if I'm interested in studying the probability, for instance, of this rare event, so that the fraction of time steps which fall into this blue band is the 80% instead of the 10%, right? So I'm going to study the probability of such a rare event, and more importantly, I want to derive the effective map that makes this rare event typical, right? Okay, so I'm going to spoil the result, because the effective map is going to be just a change of coordinates of the original map, right? And if I perform such change of coordinates, what I obtain is the following, is that the original 10 map is transformed into this pretty strange map, but now a typical trajectory has the 80% of the points within this blue band. So now the histogram is centered around the rare event. So I have made my rare event typical with this change of coordinates. Okay, so the main result of this talk is this change of coordinates, which amounts to find the topological conjugation of the original map. Right? So that's so this new dynamics is given by this FSD. I will explain why the S and why the D, and we are going to be interested in obtaining which is the gamma of S, because the F we already know because it is the original map, right? Okay, so this is now I'm going to work in explaining you why this FD takes. Good, so the main goal is to obtain the last deviation function, this exponential of minus n times I of A. And this is very hard to obtain because it is exponentially hard to obtain. So it is as difficult as computing entropies in equilibrium systems. I will emphasize in this analogy between entropies and last deviation functions. Okay, so this probability is exponentially hard to obtain, as difficult as, for instance, the probability of having an energy per particle in a given system, which goes as the exponential of n times the entropy density over k. This is just the result of inverting the Boltzmann entropy, right? Okay, so the entropy is a large deviation function. And what do we do in order to explore low entropy configurations? We change ensemble, right? And we go to the we go to the canonical, from the microcanonical ensemble to the canonical ensemble in equilibrium systems, and we do the same here. So we change ensemble in this way, but now instead of minus beta, we have minus s, which is the conjugated parameter to the observable of interest, right? So, but in this new ensemble, my rare event, which was in the far tail distribution here, is now typical, right? And in order to do that, okay, I proceed in an analogous way of equilibrium systems. So I can define a dynamical partition function, which normalizes this new ensemble. And through this dynamical partition function, I can compute the scale cumulant generating function, which is related through a Legendre transformation to the large deviation function. Okay, this, if you are not familiarized with large deviation theory, this might seem a bit overwhelming, but it's just like entropies and free energy in standard statistical mechanics. So we have a relation. This would be the free energy. This would be the entropy. This would be the partition function. And we can reduce our sampling problem to an spectral problem, as we do when we apply, for instance, the transfer matrix approach in order to calculate free energies in the 1D IC model. Right? So I can pose this sampling problem into a spectral problem, and that is what I shall do. Okay, but it is worth emphasizing in this analogy between equilibrium StatMech and chaotic maps. So in equilibrium StatMech, I have this probability of energy per particles by inverting the Boltzmann equation. Here, I go to the canonical ensemble to make these low entropy states typical by changing beta, namely the temperature. I have that this partition function goes as the exponential of minus the free energy, right? And the temperature I have to choose is the one satisfying this relation. In an analogous way, I have this slide here where I have to choose the correct S in order to match the fluctuation in this way. So S must be minus the derivative of the large deviation function. Okay, so modifying the temperature, I can make typical and likely values of the energy with a small entropy, right? And modifying S, I can make typical and likely values of my observable A with high values of the large deviation function. So how do I sample in equilibrium systems? So I applied several methods, right? For instance, the Metropolis or the Glauber. If I have ergodic dynamics and detailed balance, I can apply this kind of methods in order to sample from this exponentially biased distribution. But in chaotic systems or in stochastic or in open quantum system, it's not so simple to sample from this exponentially biased distribution. And that's the aim, to find the effective map that realizes this probability distribution. Okay, so just a bit of maths here. The evolution of the initial, the probability density of initial values is given by the Frobenius-Perron operator with invariant density rho. I have to define a bias Frobenius-Perron operator introducing this S, and by applying my eigenvalue problem, I'm going to be able to derive the scale cumulant generating function through this dynamical partition function. Okay, so I have that. This is the eigenvalue problem I have to solve in this case, right? Once I have my tilted Frobenius-Perron operator, which is given in terms of the average observable I am interested in, this G, right? I can pose my eigenvalue problem, and the largest eigenvalue here, this e to the theta of S, is the one it corresponds, gives me the behavior of the long-time behavior of this dynamical partition function, just as the free energy gives me the large size behavior of the dynamic of the standard partition function in equilibrium systems. So once I have the largest eigenvalue, I have the scale cumulant generating function. I perform the Legendre transformation, and I have my rate function. So I have the probability of getting any value of A. Okay, so it's worth comparing this to what happens in stochastic systems, because that's going to lead me to the results of the so-called dupe transformation, that is the one making rare events typical in chaotic maps. For instance, in chaotic systems, I can express the master equation in this operatorial form, right? And I can define my bias generator in this way, introducing this e to the minus s q to the rates, the original rates. So here I have somehow the dictionary between stochastic systems and chaotic maps. The probability vector of my system at time t evolves according to this generator, and the initial probability density in my chaotic map evolves according to the Frobenius-Perron. Here I tilt the generator, here I tilt the Frobenius-Perron operator. And I can, in the framework of stochastic systems, I can obtain what is the new dynamics that leads me, that produces the fluctuation I am looking for. And that is called the generalized dupe transform. All right, so just by having this dictionary, it's easy to derive what would be the dupe generator, the dupe Frobenius-Perron operator in the framework of the chaotic maps. It is worth saying that this bias generator is non-physical, so the dupe transform makes it physical in the sense that it conserves probability. And the rates in any stochastic systems are modified in this way. So in chaotic maps, what we derive is that the dupe Frobenius-Perron operator is given in this way, and more importantly, that the effective map is given in this way. Okay, so this was the motivation to show you that this was the form of the dupe operator in chaotic maps. And the invariant density in chaotic maps leading to the fluctuation I am looking for is this L times R, which are the left eigenfunction and the right eigenfunction, respectively, of the eigenvalue problem I have to solve. So I have now, I have found the target probability leading me to the fluctuation I want to reach, which is this L times R, and now I have to find the transformation over the original map, giving me this target distribution, right? So I have my original trajectory, x0, x1, until xn minus 1, with invariant density rho. I transform it, and I have to get this invariant density. And this is analogous to what we do in stochastic systems, right? And by defining the cumulative distribution, I am able to find what is the transformation to a random variable to give me another distribution that I have fixed from the very beginning, right? So from the cumulative distribution, it is easy to check that this y, this transformation, gamma s over x, is given by the inverse of the cumulative distribution of the target probability density over the original cumulative distribution. Okay, so it is rather simple, right? It is like when we transform random variables. And what about the map which transforms y naught into y1 and so on? So if I apply some maths here, it is easy to derive that this that the map driving me from y naught to y1, y2, and so on is given by this topological conjugation, right? The maths are very simple. So the message is that I have some typical trajectories here, right, with this red histogram, and I want to get the transformation that leads me to this blue histogram. This transformation is given by the green function here, this gamma of S, and that leads me to red trajectories. And if I perform the histogram of those red trajectories, I have this blue histogram, and so I have made typical my rare events. So I can go back to the original, to the first example. We applied this, and so we get what I showed you at the very beginning. And we can consider as well other kind of chaotic maps, for instance, the Dublin map, and a very simple observable, which is the average position, 1 over n, the sum of over x. So the average value, if I don't do anything, is 0.5. But if I tilt, so if I modify my dynamics in order to have a larger average value, what I get is this map, and then a trajectory, a red trajectory using this map is given by this one, which has 0.73 as an average value. So here you can see as well the scale cumulant generating function, the right eigenfunction and the left eigenfunction in this case. And we have also studied the Ulam map, right? And again, we have performed the very same procedure to the period 2 orbit, right? So this is the original map. I can tilt to make it larger or slower, and I get different maps in each case. Here, I make the average larger. It goes from 0.09 to 0.79, so it goes in this way. Here is the indicator function of these two blue bands, and here I make the average lower, so it avoids these two blue bands, so the typical trajectory takes this form. Okay, we extended as well this to the dimensional systems. We consider here the Arnold-Katz map, and well, just to show you an example that if I consider as an observable the checkerboard indicator, the light blue histogram is the original one, and I can make a transformation suitable to have a larger value as an average one, or a lower value as the average in each case, right? So take-home messages are that we have extended the generalized Hooke transform to the realm of chaotic maps, also in d dimensions, and we are then able to obtain the effective map realizing atypical trajectories in d dimension. Okay, so the outlook could be how to obtain finite time large deviations, because this is what I explained is in the long time limit, and also the continuous time generalization. Okay, thank you very much for your attention.
Okay, thank you, Carlos, for the talk. Do we have any questions?
Hi, this was a very nice talk. I'm wondering in this framework, because when one does it with stochastic noise, as far as I understand it, large deviation comes from a very unlikely realization of the noise. And here it will come like a very unlikely initial condition of the map that will give you the chaotic dynamics. So I wonder in this case if it is possible to pin down which one is the initial condition so you can see the rare trajectory in the original map and not need to transform one.
Yeah, okay, thank you. That's a very good question. So actually, we started in that direction, but we realized that as long as the map is ergodic, also the average value does not depend on the initial condition anymore, because the average value is given by the ensemble average. So it loses the information of the initial condition. So in the same way, when we change to a canonical ensemble and we fix the average of the rare event, it does not depend anymore on the initial condition. right? So we just get which has to be the rare invariant density. So we don't care about the initial condition anymore. All the map leads to this histogram that is displaced with respect to the original one.
Very nice talk, Carlos. I have a couple of questions. First of all, when you apply this procedure and you obtain a distribution for the rare event, my question is what you can learn about this distribution, about the phenomenon. For example, in the case of the Dana, this okay, suppose it's a rare event. We try to measure in the past the history of these events, and we find a nice distribution for this rare event. So from your theory and your procedure, what information we can extract maybe to prevent something like that? This is one question, and the second one is maybe related. It's possible, just not from a map, just from taking data for experimental from experiments. So you have some time series of data. You can apply this procedure to.
Okay. Thank you. Very good questions. So the first one is that what we learn is what is the say the transform dynamics that leads me to a rare event. So somehow, I mean, this is the very first step with one-dimensional maps, very simple things, right? And we already get complicated stuff. So if we consider continuous time and continuous variable, like climate models, this must be much more complicated. But what I hope is that, as well as in, for instance, in stochastic systems, what we guess when we study rare events is how the dynamics is modified. So you could see that in order to have some extreme events, the dynamic would be that way. So if in your model, your parameters are being modified in that direction, that means that we are going to be eventually there. So, the main message is that we obtain information about the dynamics, right? And in this case, the dynamics is the effective map, okay, which is transformed, for instance, in this case, from this, which is the Dublin map, to this strange one. Exactly. And in the case of the 10 map, okay, you see that this strange map leads to this rare event. Okay, so you can map them and see, according to the dynamics, what kind of rare events you would expect, right? And for the second question, I don't know. I don't know. I should think about it, but it would be very interesting. I mean, there are some prerequisites here as ergodicity. So as long as you have ergodicity, you could maybe try to figure out how you would apply this framework on what you're proposing. But I don't really know. Okay. Thank you.
If there are no more questions, okay. Then Carlos, thanks again.
Thank you.
And with this, we finished. Yes, so we finished the afternoon session. Please, if I said your name or if you have any dietary restrictions, I think, please go to the desk because they have a ticket for you for the dinner.